Hey, problem 30 is dealing with a nice little graph. You want to take a moment to study that graph just to familiarize yourself with it, because I'm not going to draw it on here. And so when I talk about certain things, at least look at the graph while I'm discussing it. So it is a potential energy graph, and as you can see, um, something in there, like one way to visualize these is if that parabola is like a bowl, and you could have a marble, let's say, on the inside of that bowl. If you let go of the marble, if you hold the marble at the top of the bowl and let go, it's going to roll down, increase in speed, right? Lose potential energy, and be at a maximum speed at the bottom of the bowl, and then increase. I guess I could draw that. Right, if you put a little marble here, it's going to drop, increase speed, maximum speed, slow down, stop, and go back down, right? So it's going to oscillate back and forth. So that's one good way to think of a potential energy graph is sort of like a profile of a bowl. Or, I mean, I guess it depends on the shape, but in this case, a parabola is bowl-shaped. So what do they give us here? They give us the mass of such a particle, 2 kilograms. They give us the US, which is the value of the potential energy at the top of the graph. You'll want to take a look at what that means. That basically just gives us the scale. There's 4 dash marks in between each digit, so that's 0.25 each, right? 0.25, 0.5, 0.751, yep. So each dash mark is 0.25 joules, and they tell us that the equation U as a function of x equals b x squared. They don't tell us what b is. We could solve it pretty quickly, right? Because we know that when the energy is 2, we know that the displacement is 20. Is that centimeters? So actually, we want to convert that to 0.2 because joules has meters in it. So that gives us a b value of 50. What's the unit for that? That would be, well, this is joules and this is meters squared, so joule per meter squared. And yeah. Oh, they also give us the velocity at the bottom here, the maximum velocity, Vmax. I'm going to label it equals. And I'm also going to convert it to meters per second. It's 85 centimeters per second, but that's 0.85 meters per second. So that's enough to get us going. They want us to find, in part A, will the particle, if the particle passes through the equilibrium position with that speed, will it be turned back before it reaches 15? So again, I'm not going to draw the whole graph, but 15 on the graph is not quite all the way, like 20 is way at the top here, so 15 is that. So the question's asking, given that the maximum speed here, will it make it past? Will this marble go up past, or this object, it could be a spring oscillating back and forth, will it go up past 15, or will it slow down, stop, and turn back before it hits 15? So let's figure that out. We get conservation of energy. We know that the total energy is the total energy is potential plus kinetic energy. And for the visualization purposes of this problem, sort of using gravity as the oscillator, but this is really just, as a function of x, whatever is causing it. So we'll just put u, excuse me, u as a function of x. Anyway, we know that down here we have the lowest potential energy. In fact, if you look at the graph, it's 0. So we know that the total energy in the system is all kinetic at the bottom. And so that is 1/2 m Vmax squared, which is 1/2 times 2 times 0.85 squared, which equals 0.7225 joules. So that's the total energy in the system. And as the whatever this object is goes up, increases in potential, it loses the kinetic and gains that potential. By the time it hits 1.1, hold on, I got a coughing fit going on here. You didn't need to hear that. So anyway, yeah, as I was saying, you start off with 0.7225 joules of energy, total energy, which is just in the form of kinetic here. And as it goes up, it decreases potential, decreases kinetic, gains potential. So really, what we're looking for is what is the potential here at 15 centimeters, and how does that compare to this energy? So we have to eyeball it on the graph. If you look at 15 on the graph and you go up to the potential energy axis, it looks like it's between 1 joule and 1.25 joules. So let's just say like the energy at the potential energy at 0.15 meters is about 1.1 joules. So that now makes it pretty obvious whether or not it reaches it. We do not have enough energy to reach 15 centimeters because we would need 1.1 joules of energy, roughly, to even get there. And so, yes, the answer to the question is, wait, what's the question? Will it be turned back before? Yes. Yes, it will be turned back before because we don't have enough energy to actually reach that point. That's part A. Part B, we are trying to find what position will it be turned back at. So we'll use this B value that we found. Actually, we'll use this function here. Ux equals 50x squared, and it's turned back, so all of the potential, all of the energy is in potential when it turns back, so that's the energy here, 0.7225 equals 50 times x squared. Solve for x and you get x equals 0.1202 meters. So it turns back at about 12 centimeters, about 3 centimeters before the 15 that it was asking for in part A. Alright, so that was a pretty cool problem dealing with energy.